Beemath en primaria de cuarto a sexto. Desarrollando secuencialmente el sentido numérico para enfocarlo en la resolución de problemas. Subitiza complementos del 10. ¿Cuántos puntos aparecen en el marco? Recuerda si una fila está llena de puntos. No tienes que contarlos porque sabes que son 5. ¿Cuánto falta a 100?
Veamos un ejemplo. ¿Qué pasa con el número 37? Si te preguntara a qué distancia está este número del número 100, la mayoría de la gente escribiría 100. Pondrían 37 debajo, luego lo restarían, obtendrían el número, finalmente obtendrían la respuesta correcta, pero hay una forma más rápida, y cuando haces aritmética mental, en realidad, todo se reduce a la eficiencia y la velocidad. Entonces, si hay una forma rápida de hacer algo, entonces realmente necesitas hacerla. Déjame escribir la respuesta y mostrarte por qué es más rápido hacerlo de esta manera. La respuesta a esto es 63. Porque 37 y 63 te dan 100. Entonces, ¿cómo lo hacemos rápidamente sin escribir esto y hacer la resta? Si te dan un número y quieres saber cuál es su complemento para obtener 100, entonces la forma más rápida de hacerlo es en esta columna. Observa que estos dos dígitos de aquí suman 10. 7 más 3 es 10. Así que suman 10. Los dos primeros dígitos de aquí no suman 10. Suman 9. Y eso siempre será cierto para cualquier número de dos dígitos cuyo complemento quieras encontrar, que casi puedes considerar como las piezas de un rompecabezas 37 y 63. Encajan muy bien porque juntas te dan 100. Y verás más adelante que eso va a acelerar enormemente tu aritmética mental cuando empecemos a ver problemas reales de suma y resta. Así que si te doy el número 45 y te digo rápidamente dime a qué distancia está de 100. De nuevo, la mayoría de la gente tendría que pensar un segundo, pero todo lo que tienes que hacer es mirar, vale, en la columna principal, ve de izquierda a derecha. De nuevo, no trabajes en la columna de la derecha, ve de izquierda a derecha. Para la columna del dígito de la izquierda, solo estás intentando sumar 9. Entonces, voy a poner un 5 ahí. En la columna de la derecha, solo intento sumar 10. Así que voy a poner un 5 ahí. Y esta es la respuesta. Ese es el complemento. ¿Qué pasaría si tuviera el número 76? Y dijera, ¿cuál es el complemento de eso? Adelante, inténtalo tú mismo muy rápido. Lo que vamos a hacer es que en la columna principal, solo intento sumar 9. Así que voy a poner un 2 aquí, y en la columna de la derecha, solo intento sumar 10. Así que voy a poner un 4 aquí, y eso es todo. Realmente no tengo que hacer ninguna resta. No tengo que devanar los sesos tratando de pedir prestado o llevar dígitos ni nada parecido. Solo estoy buscando ver qué encaja como pieza del rompecabezas.
Enlaces numéricos en unidades y fracciones.
But then they extend it into the more complex areas of adding, say, units of measure. And so this example, for a lot of American teachers, we know that we would add these two together, get 20 ounces. And then what do? We teach children to convert. And that is really dividing, and it becomes a procedure. But let's look at an intermediate step. And again, compensation or part-whole thinking. So a student would do this, 14 ounces plus 6 ounces. They're now at a, we're a few grades higher than first grade. And they would realize, I'm going to get 20 ounces. I'm going to go over 1 pound. So they start to think, okay, much like we did the number one before. Now, my next unit of measure is 1 pound. So the student thinks, how many ounces from the 6 do I need to complete a pound? I need 2 ounces. And then what's the other part that's left? 4. So what do I have? I have 1 pound, 4 ounces. This is a step used in between adding under ounces less than a pound and before converting units of measure. So this part-whole thinking is very valuable. It builds understanding. They also use it, for adding time, units of time, inches and feet, all of that. Complete one whole unit and then what's left over. But I want to show you one more example that I believe to be very, very powerful. And now picture we're adding 5/7 plus 4/7. Typically what we do is we would get an improper fraction. We would get 9/7. And once again, what children learn to do as a procedure, they learn to divide 7 into 9, and they get one group, and they get 1 and 2/7. So what I mean is this is the procedure to convert an improper fraction to a mixed number. I want you to watch an intermediate step here again, emphasizing mathematical thinking. Now a student realizes they're going to go over one whole unit of sevens. So they're going to ask, how many sevens do I need from 4/7 to complete one unit? I need 2. So how many are left? 2/7. So I have 1 and 2/7. Understanding versus simply doing a procedure. So one thing this afternoon, one feature or strategy I wanted to share was this idea of using number bonds through the grade levels, if you will, to reduce complexity and emphasize understanding. That was for addition. Another strategy they use that I want to share with you has to do with subtraction. And of course they learn they learn multiple models. They use Zoltan Dienst's philosophy of multiple models to understand different concepts. But now they're at the point in 3rd grade where they're subtracting 3,267 from 5,000. They've learned the algorithm. They've learned why the algorithm works, so they know why it works and how it works. But a child with true number sense would look at this and say, this is going to get me into serious trouble, subtracting across zeros. So watch again what would have happened in earlier grades. Something like this with single-digit numbers. I might, with the young students, say, well, let's subtract, and if we take 4 from 6, the difference is 2. And then what I might do is to say, well, let's add 3 to the minuend and 3 to the subtrahend, and what do we get? 9 take away 7. What's the difference? Still 2. Well, let's subtract 4 from the minuend, 4 from the subtrahend, and we now get what? 5 take away 3. And what's the difference? 2. Why am I sharing this with you? Because this is what takes place earlier, where children actually themselves come up with a rule where it doesn't matter. You do not change the difference when you're subtracting as long as you add or subtract the same value to the minuend and the subtrahend. So once they see how this works, watch how we can apply it to a problem later on. A student with number sense would say, guess what? I know a better way. If I subtract 1 from the 5,000, I now have 4,999, which means I must also take 1 from the 3,267, so 3,266. What I've created is a much friendlier number, 1,733. I had a teacher recently come to an event where I was speaking and tell me that her school went up an entire stay line just based on this one strategy. But it's not a trick, and I hope you see that. The other example of subtracting with compensation is, and I'm going to show you one. Many teachers, again, if you're watching this, you're going to know this student because I taught them myself. 23 take away 18. Children who only learn procedures see the subtraction sign, and usually this is what they'll do. 1 from 2 is 1, 3 from 8 is 5. And what I always say on a multiple choice exam test, this will always be an option for students to answer. So typically this is what can happen. But watch what we're going to do. I'm going to show you, again, using that earlier rule that they have discovered with single-digit numbers. They would look at this, and I'm not subtracting, I don't have zeros, but I am regrouping. So they're thinking. And you know what? What they would have known, too, is that if I'm subtracting a multiple of 10, it's much more friendly to subtract. So what do? If I add 2, I can then change the 18, add 2, and get to 20, which means I must also add 2 to the 23 to get 25, and my difference is 5.
Valor posicional en primaria de cuarto a sexto.
Hi, and welcome to Understanding Place Value. Before we get started, remember, your most important asset in learning mathematics is your teacher. Having said that, let's get started. Let's start with what you see falling on your screen. These symbols are the symbols used to represent the numbers in our number system. Any shape, mark, well, anything that represents a number can be called a numeral. The word numeral is used interchangeably with the word digit. Just as there are 26 letters in our alphabet used to represent every word imaginable, the 10 digits up on your screen represent all the numbers in our base 10 system. How can we let 10 digits confuse us so much? Let's understand how these digits get their place value. The base number in describing place value is how many numerals we have to work with, 2 of which will be 1 and 0. Another way to understand this is we work in groups defined by the base. For us, that would be groups of 10. Let's see this in action. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Hey, well, that didn't work. Let's try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What happened is we set a place value to represent one group of 10 single items, which we call 10. Here the 0 has no value and serves as a placeholder to represent the number 10. Let's try that again, this time counting up in the tens place. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. What happened is we set a place value to represent one group of 10 groups of 10 single items, which we call 100. Here the zeros have no value and serve as placeholders to represent the number 100.
Okay, so far we understand we use a base 10 number system. Because it is a base 10 system, there are only 10 digits to work with, 2 of which will be 0 and 1. To have these digits represent different values, columns are created. Each column represents a different place value. To understand place value, look at the digit you see, the column it is in, and what it would be multiplied by to give it its value. Remember, work in groups of 10.
Every time we count up a group of 10 single items, we advance one more in the column to the left. So any digit you see in the tens place is multiplied by 10. Count up 10 more single items, we end up with 2 groups of 10 single items, which is 20, and so on. This grouping up of 10 single items goes on and on. As you should know, the digits in the ones column represent themselves, and anything multiplied by 1 is itself. This is key in understanding place value. So, any digit in the ones column is multiplied by 1. Any digit in the tens column is multiplied by 10. Any digit in the hundreds column is multiplied by 100. This goes on forever. Think about that. If we could travel to the end of the universe, or space as we know it, behind that wall would just be more space. It's mind-boggling. Anyhow, as the numbers got larger and larger, the mathematicians created something called exponents. Maybe you heard of it referred to as to the power of. When a number multiplies itself by itself is the beginning of understanding exponents. Let's understand why we broke numbers down into expanded notation. We start with a simple number minding its own business, and then we complicate things by taking each individual digit and have it stand alone to represent its place value. As we dissect each number further, you will agree each equation to hold true. As explained earlier, because we are working in a base 10 number system, each digit you see, with the exception of those in the ones place, is multiplied by 10, or a bunch of tens, which are all related to the position or place they are in. So why expanded notation? If you notice, the number of zeros you see are directly related to the number of tens that multiply the digit in every place value. You see 1 0 after the tens place, and any digit in the tens place is multiplied by 10. 2 zeros after the hundreds place, and any digit in the hundreds place is multiplied by 100, or 10 times 10. 3 zeros after the thousands place gives us 10 times 10 times 10. And for the 10,000s place, the 4 zeros represent 10 times 10 times 10 times 10. I know you're tired of hearing this by now, but that just means you understand it. Let's look at the trillions place. Take notice of the commas, how they show up in every third column. This standard was created to keep track of all the zeros. So a trillion is 1 times 10 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 times 10. I'm getting out of breath. Any number multiplied by itself is how we create exponents. In this case, there are 4 groups, each containing 3 zeros that give us a total of 12 zeros, or 12 tens multiplying each other, which can be written as 10 to the 12th. So which do you want? And don't forget, numbers get larger than these. 1 times 10 times 10 times 10. Oh, I know, let's just say 1 times 10 to the 12th. Back to the numbers used more commonly, 10,000 is 1 times 10 to the 4th. 1,000, 1 times 10 to the 3rd. 100, 1 times 10 squared. 10 equals 1 times 10 to the 1st, because any number to the 1st power is itself. And 1 is equal to 1 times 10 to the 0, because any number to the 0 power is 1. 1 times any number does not change that number, so let's simplify. That's better. Why is any number to the 0 power 1, yet 0 to the 0 power is not? Why can we multiply a number by 0, but to divide by 0 is undefined? I think it's time I speak about the rebel within the digits. The digit 0 kind of follows its own agenda. We all understand 0 to be null, nothing, nada. This is nothing. That rebel in the car is the digit used to represent nothingness.
Singapur Math en primaria. Cálculo mental sumas con 3 dígitos.
¿Puedes sumar estos tres números en menos de 5 segundos? 367 más 728 más 32. Tienes 5 segundos. Adelante. Se acabó el tiempo. ¿Obtuviste la siguiente respuesta? 1227. Si lo hiciste, felicitaciones. Bien hecho, esa es la respuesta correcta. Si no, bueno, estoy un poco decepcionado, debo decir, pero no pasa nada porque durante los próximos minutos, te mostraré la mejor estrategia para sumar mentalmente este tipo de problemas. Entonces, para empezar, lo más importante al sumar mentalmente es que no vamos a sumar de la manera habitual que probablemente te hayan enseñado, donde empezamos por la derecha, sumando primero las unidades, luego sumamos las decenas y finalmente sumamos las centenas, moviéndonos de derecha a izquierda. En cambio, lo que haremos es lo contrario. Vamos a sumar de izquierda a derecha, comenzando primero con las cifras más significativas, las centenas, luego sumando las decenas y luego las unidades. Como dije, vamos de izquierda a derecha. Creo que la forma más fácil de explicar esto es que te lo muestre. Empecemos con un ejemplo más fácil. Volveremos a este, lo prometo. Un buen ejemplo fácil para empezar. 589. Y a esto le sumaremos 637. Como dije, empezaremos por la izquierda sumando primero las cifras más significativas. Empezaremos por las centenas y nos moveremos hacia la derecha. 600 más 500 es 1100 más 80 es 1180 más 30 es 1210 más 9219 más 7 es nuestra respuesta. 1226. Fácil. Como pueden ver, vamos progresivamente hacia la derecha a medida que sumamos, lo que nos permite pensar en el problema más en el orden en que se va a responder, dándonos primero las cifras más significativas. También pueden notar que he dado más pasos de los necesarios. Podríamos haber empezado diciendo 580 más 600 es 1180 más 30 es 1210 más 16226. Es muy fácil sumar de izquierda a derecha, que es la clave para sumar números mentalmente con éxito. Con la práctica, resolverás este tipo de problemas con facilidad. ¿Qué te parece si te doy algunos ejemplos que puedes intentar? Empezaremos con un ejemplo sencillo. Es bueno que vayas subiendo poco a poco. Probemos primero con 784 más 321. El segundo es un poco más difícil. 482 más 736. Acertarás. Ahora, vamos a ponernos manos a la obra con el tercero. Empezaremos sumando tres números. 927 más 740 más 278. Por último, volvamos al ejemplo original y probemos. Eran 367 más 728 más 132. Y creo que podrás hacerlo en menos de 5 segundos. Pero no te presiones. De todas formas, pausa el video si quieres probar estas o vivir peligrosamente y responderlas a medida que las voy haciendo. Por cierto, si te gusta este truco, hazme un favor, pulsa el botón me gusta y deja un comentario. Y, por favor, hazme saber si te ha resultado útil este truco. De todas formas, ya es demasiado tarde para pausar. Vamos a ver estas respuestas y a ver qué tal eres. Bueno, primero, la más fácil. 784 más 321. Entonces, 700 más 300. Ahora, mira, no voy a decir más cada vez. Voy a llevar la cuenta, ¿de acuerdo? Entonces, 701.001080.101.15 es nuestra respuesta. El siguiente, 1100.180.210.218. ¿Te ha parecido bien? Como he dicho, es una forma muy rápida de sumar mentalmente. En nuestro tercer ejemplo vamos a sumar tres números. Vamos a hacerlo. 1600, 1800, 1860, 1930, 1937. Y nuestra respuesta es 1945. ¿Qué tal te ha ido? ¿Has sacado 3 de cada 3? ¿Te has acercado a los 5 segundos? Eso espero. Volvamos al ejemplo original. Mira lo rápido que puedes sumar. Tenemos 1100, 1080, 1210, 1220, 1227.
Problemas en palabras.